really excited to be starting. And like I say, I hope soon we'll get to have more interaction, because I know there's a lot of people around who are interested in similar things and who I'd like to discuss with. So yeah, and just to echo what Jamie said, please interrupt and ask questions and stuff. I wasn't exactly sure what the audience was, so I planned a kind of general talk about talking about applications of higher dimensional category theory in computer science. And because of that, I'm gonna start off very generally. And so I hope it can be informal in the sense that if people have particular questions or whatever, don't hesitate to ask or anything like that. And I should say my background. So I originally studied pure mathematics. My background is in homotopy theory and coming from topology, but I had always maintained an interest in computer science. I learned to program at a very young age. I've always been interested, and so the past probably so since the introduction of type theory by Voevodsky and Awadi and some other people, I've been thinking a lot about type theory and its connection with algebraic topology. And so most of what I'm going to say in at least this first part of the lecture is really motivated by those developments, by the realization of how close type theory is to higher category theory, higher topos theory, and these kinds of things. And I'm going to sort of detail some of those things, but I'm going to speak very generally about them. And I also, maybe it's been a sort of pet project of mine or pet idea of mine in the back of my head for growing for the past couple years, is to try and disseminate some of these ideas in a more general fashion, to sort of see some of these ideas from higher category theory get out there in the computer science community more generally, as opposed to just confined to formal proof assistance and synthetic homotopy theory, which I think has been a big sort of part of a lot of what's happened with these tools. And so because of that, so let me just start from a very general place and just ask the question of, like, what does equality look like in programming languages today? What does it look like? And I would say most programming languages furnish you, first of all, with hardware or physical equality, both of numbers, say primitive types or something like this, as well as usually if you have some sort of reference type thing, if you're an object-oriented language, or even some languages like OCaml have a notion of physical equality, something like this. So the equality inherited by the machine, which we typically think of as the classical equality that everyone thinks of when they think of equality, which is Boolean valued, a yes or no answer to a question. And then from there, you're typically given user-defined equality on user-defined types, which is to say that if your programming languages allows you to define new types, maybe record types, maybe some types, maybe it's object-oriented, so it allows types by definition by classes or things like this, you can ask when you introduce those new objects, how should we compare them? This is a very sort of fundamental question that you want to ask, and usually these are treated by in ad hoc ways. So, for example, in functional languages like Haskell, you usually have type classes like EQ, and in languages like in object-oriented languages like Java or Scala or Kotlin or JavaScript or something like that, you have equality methods. The important thing about these things is that they are the wild, wild west. Let me say it that way. It's the wild, wild west, which is to say, you can define whatever you want as equality intertypes, and which is, I mean, some people obviously like flexibility. Some people don't like type systems at all, so that's fine. But obviously, for people who are interested in type systems and things like this is a kind of surprising state of affairs, that something as sort of primitive as equality is completely ad hoc. And so you might ask if there's anything we can sort of do about this. By the way, I should say, I mean, there's some sort of consequences of defining equality this way, which is there are no guarantees.
Just like a really concrete example, I mean, do you mean something like, I mean, we could compare strings in a
Right.
case-sensitive or case-unsensitive way? Do you mean that sort of?
Sure, exactly. I mean, in yeah, I have guarantees. I have so much trouble with the word guarantees. I'm not sure why. Anyway, yeah, exactly. So I mean, in Java, for example, every object has an equality method, and you define it to do whatever you want. Um, and similarly, I mean, even in a language like Haskell, where you have type classes, where you can say my type supports an equality, you can, in principle, define that equality to be whatever you like it to be. Now, in modern languages like Haskell and OCaml, functional languages and stuff, where you have algebraic data types, there's usually a canonical choice. And so many modern languages will let you say, opt for the canonical choice, which is by recursion, compare the components of each of my algebraic data types. So this is a good choice. It's the choice that actually, when we talk about more complicated type theories, is usually the sort of canonical choice. But in say object-oriented languages, this is totally different. There's no such thing, and you can define equality however you want. So you get no guarantees of well-formedness, which is to say the classical ideas of symmetric, transitive, and reflexive. So in principle, when you implement your equality method, you should make it symmetric, transitive, and reflexive. But of course, the compiler can't help you with this, and there's not really much you can do about this. And I submit, although one day I'm going to go searching for the internet, scouring it for bugs, but I submit that this is the source of a number of software bugs. The fact that you're allowed to compare things in any way you want, and it's easy to break some obvious rules of comparison, of well-formedness comparison. So you don't get any guarantees that your equality method is well behaved. Neither do you get no guarantees that functions, even let me say even effectless. I mean, because I'm aware that real programming languages have effects, and that complicates the issue. But that even pure functions respect equality. So you declare your function, your equality on some type. Sorry if my handwriting is really bad. It's I've never tried this before, and I'm talking at the same time. So tell me if you can't read anything. It says respect equality there. Anyway, so you can define a function on a type, and you can have declared the equality on your type to be something that you calculate. And then you can have another function which just does different things on things that you declare to be equal. And that's kind of a surprising behavior in some sense. And again, pure functions, there's complications when you talk about having effects like IO and stuff like that. But even pure functions in something like Haskell or OCaml, there's no guarantee that they respect the user-defined equality type. Right. And so worse, it's not even always clear. So I should say that in most of these languages, equality is modeled by, however you express it in the type system, some function to bool, some function which takes an element of your type and returns a Boolean saying yes or no, these two things. Oh, I guess it's A to bool. So it takes two elements, maybe A cross A to bool, depending on how you set it up. So it's not even always clear that such a function exists, or how it should be defined. So, and in fact, there are known cases where it can't. So if you think about sort of constructive real numbers, for example, this is an example where such an equality can't exist for sort of computational reasons. You can't compare an infinite string of digits, because when do you know that they stopped being equal? So there's some kind of there's obstructions like this, computability reasons. Even if you've ever tried to implement one of these equality methods in some random programming languages, say in Java or JavaScript or something like this, there are all sorts of ambiguities that arise very quickly as to how the function should work. If I have some complicated graph of objects holding references to each other, should I follow that reference graph? What if I start off comparing two objects which aren't at the same point in that reference graph? What if my object has a list of objects inside of it with references? Should I take into account the order of that list, or should I not take into account the order of that list? And it's not even clear in many situations that there's even a sort of good answer to this question. So if you sort of look at this state of affairs, you sort of realize that equality is kind of a little bit of a box of worms in modern programming languages. And I mean, to some extent, we've sort of come to expect this maybe, but as theoreticians or whatever, I think we should ask the question is if we can do better.
Eric, can I make a comment?
Yeah.
Yeah. So I mean, on this slide, you're talking about equality, as it were, from the programmer's point of view, using the programming language.
Yeah.
But of course, there's an even worse problem, right? Is even if the programming language had no pretension whatsoever to provide notions of equality for the programmer, there would still be extreme difficulty in understanding what it means for two programs to be the same.
Sure. Yeah.
So that's a sort of one level higher up. There are big problems, as it were.
Yeah. That's another box of worms is understanding what equality of programs should even mean. So I totally agree with that. Right. Okay. So so this is just my state of affairs. And like I say, my goal in saying these things, which are very general and stuff, is to start asking what happens when we start to look at this state of affairs of equality and ask what we can do about it. And right. So an example that I have in mind is graphs, right? So graphs. So graphs are clearly something, and I'm just thinking of, say, directed graphs to be concrete, right? So actually, let me change this thing because I'm going to do it the other way. So a question is like what should a type of graphs look like, and how should we compare graphs? So modern, many algorithms operate on graphs in computer science. Is one of the most it's an extremely important data structure. And how are they represented? So most often represented by, well, there's a couple of choices: adjacency matrix, or another popular choice is adjacency lists, and so on. So there are various ways of representing. So basically, what you do is you give your graph a number if you don't know what the matrix, and then you just count the number of arrows from a particular vertice to itself. So 0. I guess my matrix looks like this. Is that right? It looks like the thing I did. So you're most often you get some representation like this. You can imagine defining a type which holds values of this. There's lots of different choices. But when you start to look at this and you ask how should you compare two graphs, things start to get a little bit murky. How should you actually compare these two graphs? Because on the one hand, you have this adjacency matrix representation, but it did something which is a little bit strange, because to represent it as a matrix, I needed to sort of number the vertices, but that's not part of the notion of being a graph. If I were to, for example, switch, switch my colors and call this one 1 and call this one 0, my matrix would change, but my graph wouldn't, because this was just a choice of the order of how to.
I guess in this example, the matrix doesn't change, but obviously in general.
Yes, I think not a great example for it.
So I want to, yeah, exactly. So
a very picky audience here.
That's right. But you get the idea. So by storing this as an ordered list in memory, I've made a choice about my graph, which was a little bit strange. So should that be taken into account when I compare equality of graphs? And worse than just the total order is the fact that graphs, and this is why I drew this graph here, they can have symmetries. So this graph can be isomorphic to itself by interchanging 0 and 1. in a sort of non-trivial way, which is not just changing the order on vertices, it's actually moving the graph, right? So if I did a non-symmetric graph sort of like this, now I can't, the graph does not have an isomorphism to itself, but I can still choose to order the vertices in a different way. So there's a kind of ambiguity about how to represent sort of a graph, and it's not exactly clear how you should compare them. And what ends up happening is that the comparison that you use on graphs is not really well adapted to the particular semantic domain. It's not a comparison of graphs. It's a comparison of their presentations. And of course, this is not to say that people aren't aware of this problem. People absolutely are aware of this problem. It's not. But in practice, then, if you write an algorithm on the type of graphs, in order for it to really be a function on graphs, you should verify that it doesn't depend on the choice of representation, right? And because modern sort of type systems don't have rigid, nice sort of structured notions of equality, there's no way to make this clear to the type system at all, that you've written a function on graphs and not on presentations of graphs. And I maintain that those two things are sort of different from each other. And I'm going to argue later that graphs, the type of graphs should definitely exist, but that it's not a type that admits this sort of Boolean comparison, and shouldn't admit this sort of Boolean comparison. The type of equivalence classes, of isomorphism classes of graphs, does admit a decidable equality, but the type of graphs itself doesn't, and I'll sort of come back to that. So the crucial thing here that I sort of want to get across is so then what is the natural notion of equality of graphs? And I sort of posit, this is me coming from sort of univalent type theory perspective, that the natural notion, I underline it because this is a little bit notion of equality of graphs is isomorphism. So when I say that two graphs are sort of equal to each other, I should mean that I have specified a way to set them equal to each other. And in the symmetric graph, we see that there may be more than one way. So the surprising thing when you first hear someone say something like this is that this immediately goes out of the realm of the equality that we're all used to, saying two things are or aren't equal. And we arrive in a realm where equality may be multi-valued. So equality may be multi-valued. Okay, and this is at first maybe a strange thing, but my opinion is that it starts to look better and better the more you actually get used to it. You get used to this idea. Okay, so this is my sort of running example that maybe. So
can I just understand? So when you say equality is multi-valued, you mean now I think of it as a function which, given a pair of graphs, gives me an actual isomorphism, or
so that's what I'm about to change. So let me maybe the next thing I'm going to say maybe will answer your question. Okay. So that is a decidable question, right? Computing whether two graphs are isomorphic. So it may sound. So let me clarify what I mean. So okay. So So if you have this idea in your head and you want to address what I was saying before, that that we have type systems, but because of the way we implement equality, the notion of equality can't interact with the type system, because our notion of equality is just defined as a certain kind of function, a function with a certain type. So in order to have a more refined type system that could take into account equality, what we can do is we can take the approach of Martin Löf and we can reify equality as a type. Okay, so for any type A, I can ask to be in a language where, and given any two elements of my type A, I can ask to be in a language where there's a new type, which is the type of identifications of A and B. And what this does is it takes equality out of the realm of something you can compute, so a function that you might ask to return true or false, and it does exactly what I just said. It turns equality into data. So to have a proof that two things are equal is to produce an element of a different type. And if we think of types as sort of places to store data, well, or programs as well, then the elements of this type are witnesses. And then if I make this step and ask that equality become a type itself, then there's absolutely no problem of having multiple inhabitants of equality. Okay, when the equality becomes incarnated as a piece of data itself, the objection that it's sort of that I can have more than one goes away. And to create, in the specific case that I'm talking about, to create an element in the identity type of graphs is to describe a graph isomorphism. And so that makes perfect sense as soon as you're in a situation where the next thing that I'm about to write is true. Equality is data. Okay. So the nice thing about this is then this brings equality into the realm of type theory, right? So this is something that most languages can't do. So one reason is that this is probably not so common, is this requires dependent types, which is the first sort of most obvious objection or whatever. So if I want to have a type of equality between two elements of another type, then I need to be able to talk about types depending on terms, and I need to be in a situation with dependent types. My personal opinion is that actually dependent types, many languages in use today are extremely close to having dependent types. I don't think I would say they're completely adopted, but languages like Scala, Haskell, OCaml, these things, they have things that very push the border of dependent types, and these are really being used in industry. You find Stack Overflow questions about this kind of thing. So I don't think dependent types are such a these days, I don't think they're so far from something that can really be used in concrete programming languages. Okay, so right, so this is my just first advocation for, I think this is a useful thing to do. So another thing to point out is via propositions as types, we view type systems as logics for describing programs. And so it's also, when I say it's kind of surprising that we don't treat equality, that's what I mean, is that all of our simple type systems, languages that have simple types, the number of things they can say is somewhat impoverished, because in particular they're lacking the logical statement that is sort of the statement of mathematics, which is to say two things are equal. It sort of can't be expressed in systems like this. So by reifying the notion of identification as data and making a type itself, you make it amenable to discussion by the type system. Does that make sense? So that's my sort of my pitch for the fact that, I think this idea of reifying types as data can be thought of as something, as a goal more broadly in computer science, to think about this in terms of language design and things like this. It doesn't have to be relegated to formal proof assistance. I think, yeah. So I'll give some more examples in a bit. So any questions up to this point? Okay. So people have done this for a long time. So this kind of thing is this kind of idea was added by Martin Luff in his Foundations for Constructive Mathematics 30, 40 years ago. Maybe more than that now. Maybe, yeah, it's been from the 1980s, right? So
1970s actually.
1970s even, yeah. But the identity type was maybe late. Anyway, in any case. So what happens when you do this? So I think another reason that this kind of thing isn't more broadly in use is that actually it's difficult to understand what happens when you do this. The notion of identity gets very complicated very fast, and there have been hundreds, I would say, of papers in the intervening time examining equality and sort of what it means. And I think my personal opinion is that the introduction of homotopy type theory and the connection with topology brings a lot of order to this debate. So I'm gonna debated, maybe not the right word, but this subject of studying what happens to languages when we do something like this. And so as I said, one of the curious things that happens when you reify equality as data in this point is that you have to give up the notion that equality be unique. And that's a kind of surprising thing at first for a lot of people. And a second thing that happens is something. This notion of equality runs away with itself, because if you assert that every type in your system has equality, then the type of equalities also has equality, and the type of equalities also has equality. I'll just do one more: ID, XY, PQ, AB. You see, if I have a notion of equality that I can iterate for any type, then I can really iterate for any type, including itself. And so what happens is this simple idea runs away with itself immediately, and you find that that your type A, which started off very innocuously as just as you thinking it was the integers or something like that, suddenly has infinitely many levels of equality. And this is another thing which is somewhat shocking when you, like, at least compared with ordinary mathematics based on set theory, that you could have these higher kinds of things, and what should they possibly mean? And so about, I guess, is maybe 10 years ago, a mathematician, Blavatsky and Steve Aoudi, some other logicians, and kind of recognized that this structure actually does come up. It is known in mathematics where situations where you might have these infinite levels of equality, and it comes from topology, and that there's a simple way of understanding, of organizing your thoughts about how these equalities should behave, which is if I had two elements of a set X and Y, and they were equal to each other, well, then I probably wouldn't bother writing them as distinct. I would just write them in sort of ordinary set theory. They're the same point, X and Y. There's nothing interesting about them. But if I'm in a system where, oops, I didn't mean to do that. If I'm in a system where I can have more than one equality, this gets a little bit confusing. And rather, what I should do is I should think of my equality as a path between X and Y. And this way, I have space to have more than one path, so it need not be unique. And more than that, I have a place to put or to understand what it means to have an element. If this is P and Q, these are two different identifications of P and Q. Then I have a place to sort of put identifications of the next order, identifications of P of Q. And we start to get pictures like this, and I can start to think topologically about these cells. And so this kind of idea, this leads to the connection to thinking about constructive, I'm going to say it like that, equality in terms of what people call infinity groupoids or homotopy theory, homotopy types. And now I'm gonna real quick try to explain what I mean by that. So if you if you're not aware of this concept, let me try to. So the interesting thing when you do this is that it should not be the case. Your notions of identification don't live in a vacuum, because if you have two things which are identified, if X is identified with Y and Y is identified with Z, then the ordinary notion, remember, these were supposed to be witnesses to equality. So the fact that equality is transitive should mean that that there's a composite function witnessing that X is equivalent to Y. So the thing that happens is that these identity types have structure. They should have a bunch of ways of composing and whatnot. And this is the key to uniformizing your notion of equality inside the type system, which is that so can define mathematical or behavior of identity, of equality, once and for all by specifying what is the structure inherited by identity types. So this is somehow the way out of this situation where identity or equality is left to whoever wants to define whatever they want, and we incorporate it in the type system by specifying once and for all what is the structure of equality. And so what I'm saying here is that structure is very rich. It includes so that structure is higher analogs of reflexivity, transitivity, and symmetry. Oops. Okay. And so specifying those laws. So I should say, so Martin Luff gave some simple rules for generating this structure. Which is nice. So we know rules that handle how equality should behave in all of these levels. So it was an interesting discovery, however, to notice that those rules are the same as something mathematicians had been studying for a long time called infinity groupoids. So let me now just say just a quick word about what that means. So so you can arrive at the notion of homotopy type in a couple of steps. So you might start out, when you first start learning about topology and the structure of spaces mathematically, you might start out with something like, say, a metric space, which is a space with distance, where you can compare the distance of 2 points. But then you very soon start to realize that the notion of continuity doesn't depend on a metric. And many of the things that you talked about with respect to continuity don't actually need a metric. So then you you forget the metric and you remember the neighborhoods of various points. And so you by a process of abstraction, you forget that you can measure between 2 points, and you just remember which points are close to each other. It turns out, though, that you can even forget which points are close to each other, and you can simply remember which points are connected by paths. Right, so my arrow here is a process of forgetting. So I'm going to take my topological space, and instead of remembering if x is close to y, I'm just going to remember if x is connected by a path to y. So it's a much weaker notion. But in order to do this, but in order to keep a sort of a good notion of space, I'm not only going to remember when two points are connected by a path, but also when two paths are connected by a path, and when two higher paths are connected by a path, and so on. So this is what this notion is what mathematicians call a homotopy type, a space where you've forgotten any notion of nearness or distance or anything like that, and all you remember is paths and the algebra that they satisfy. So again, if I'm in a topological space, paths have a structure, have an algebraic structure, because they can be composed and whatnot. So this is the source of the connection, and it was sort of realized that Martin Luff's rules for identity types are the same thing in a kind of very precise way as a certain, but it's okay, a definition of the algebra. Oops, the algebra of higher paths. Okay. Right. So you can think of a homotopy type as this infinite sequence of possible paths between paths, and so on, together with the algebraic structure which says how these paths compose. And it turns out as a sort of miraculous coincidence that the rules that Martin Luff gave for his identity types and the rules that Grothendieck gave for defining these objects, which are notoriously difficult to define, turn out to be the same. So I sort of maintain, in a certain sense, that that this kind of rule, this structure, is in a certain sense inevitable whenever you reify equality as data. So if you want to speak in a situation where equality is given a representation, and you want to answer the question, what property should that, or what structure should that representation have, I think you will always tumble on this kind of idea. In the same way, if you ask what relation should equality have as an ordinary relation, you're going to very quickly arrive at the notion of transitivity, symmetry, and equality. So for me, this coincidence between these rules for identity types and these rules for homotopy types arises from the fact that I would say that this notion of homotopy type or infinity groupoid or type with identity types is the sort of correct notion of constructive equality. So when we're in a situation where proofs are real, real objects to be manipulated, we will, in a certain sense, always arrive at this definition, which is why I sort of advocated at the beginning that even if we want to consider very concrete programming languages and ask about how to enrich their type systems with thinking about well-structured identity, we will tumble on some of the main problems and complications that arise from this kind of definition. Okay, right. So understanding constructive equality is the same thing is the same thing. How do I want to say this? Wait, okay, is the same as understanding the structure of infinity groupoids. Okay, and as I say, I think this is a very my personal feeling is this is a robust statement. This is and so when we have troubles with the difference between intentional equality and extensional inequality and things like this, this comes down to understanding the properties of constructive equality. Okay, so let me say a couple surprises. So some lessons from topology and some things that happen when you put yourself in this situation. And I should say, like I think people who were dealing with the identity type for a long time, they were aware of the strangeness that it has as compared with a traditional notion of equality. When equality becomes data, it starts behaving in sort of strange ways. And this connection with topology clarifies, I think, some of those, a lot of those ways. Okay, so right. So some good things and bad things. Okay, so one thing you learn from this connection with topology, you can predict the behavior of types. So for example, a classical topological argument says the following: if you give me a bunch of points, and you give me some, and you right. So every point, because equality is reflexive, every point in a space has an identity morphism. But because we are allowing types to go on forever, so this is every element. There's always a canonical element in the identity type of any point when I set x equal to x. There's always a canonical element, and you can think of this element as being filled in. So a classical argument from topology says that if you have, sorry, actually, I wanted these to be the identity here. If you have two endomorphisms of an identity, degenerate thing, then there's actually, and you compose them horizontally. Actually, I could compose them vertically. That's what I want to do. Identity, and I have beta. So I'm in a situation where I have two cells, which are endomorphisms of the identity, and I can compose them. Then actually, this composition is commutative. Okay, and so what I want to say, the reason I bring this up is that this is a generic feature of constructive equality. Iterated equalities are associative. And I think that's something which sort of comes out, something that you predict from knowing this topological interpretation. And the reason is it has a very nice topological proof, which sort of proceeds in various steps, which is that you put alpha here and you put beta here, and you insert a trivial identity cell here and a trivial identity cell here. And now you rotate alpha and beta around each other. Identity alpha. Let's see if I can do this. Identity alpha, and then I go one more step, and I get beta here, and identity here, and alpha here, and identity here, and then finally I collapse out my my identities, and I get to beta composed with alpha. So this is a very, you can see it's a very topological argument, but as I say, any system having constructive equality which satisfies the higher analogs of reflexivity, transitivity, and symmetry will have this relation. Okay.
Sorry, Eric, can I just ask, did you need that penultimate step there? Or could you
maybe not. Sorry, I'm being very, yeah, I wasn't trying to be minimalist in any.
Sorry, I was wondering if you did something.
No, I'm sorry. Yeah, I went very fast. Right. Yeah, sorry. I was just drawing the topological argument, trying to see that alpha and beta sort of just twist around each other here. How do I get my red here? I mean, the idea topologically is very simple. I just twist them around each other, and I arrive at the other side. Okay, so that's one good thing. So you can predict, we can study, we can expect the properties that this kind of constructive equality will have by passing back and forth across this interpretation. So here's some other sort of surprises which come out of this. So structures, what am I trying to say? So algebraic structures on homotopy types are complicated. And what I mean when I say that is, in a constructive, what I'm asking is just very generally, what is it like to do algebra in a constructive setting? And if you are in a setting where equality is relevant, where equality is data, then what I claim is that your classic algebraic structures become much more difficult to describe. Why is that the case? Because now algebraic structures should specify their relations in all dimensions. So in other words, if I have a particular structure on one of these homotopy types, on one of these infinity groupoids, it's not enough to just say what happens to that structure after one level of equality. What I need to do is I need to say what happens in order for the structure to be well behaved. I need to say what that structure does on all levels of equality. What are all the relations? So as an example, if I have the notion of a monoid, so I have a type and it has a multiplication, then the typical thing that one would do is ask that this multiplication be unital, right? So multiplying x by some unit object should be x, and associative. So m x y z is m x m y z. So in order to have a monoid, we might ask for these two equalities. But this is only equality at dimension 1. And so the proper notion of monoid, when I have an infinity groupoid, and this is sort of well known from higher, that this list becomes infinitely long. I need an equation in every dimension to say how these things interact. And this also is well known in formal proof circles, in type theoretic circles, that if you take the naive notion of monoid, you have less theorems, because at some point you will need to know that various versions of associativity are equal to each other. And without having specified that as part of the structure, you don't get it for free. So this structure on a homotopy type in mathematics, mathematicians are well aware of this problem. It goes by the name of an A infinity space, where I complete it to infinity, whereas the version which only includes the first 2 levels, this is sometimes called an A2 space. And there's a very, very big difference between the two. Okay, so I just want to say, so this is what I want to say, that algebraic structures are more complicated. And so this has kind of some consequences, right? So for example, if we think about languages like Haskell and Scala and Kotlin and things like this, so a lot of these modern functional languages, you'll find libraries for algebraic structures, which include monoids and monads and the like, right? And typically in almost all of these, modern languages like Haskell and Scala and stuff, people use these abstractions. People really make use of these algebraic structures in programming today, but they don't do the laws. And they don't do the laws for 2 reasons. One reason they don't do the laws is because in most simple type systems, there's no way to express them. So that's fine. But the lessons of constructive equality tell us something which is a little bit shocking, which is that even if they could express the laws, the naive 3 laws for a monad are not enough. There's actually infinitely many more laws that are being missed in the situation of being in constructive equality. So I think this is something that topology sort of teaches us that's not apparent, that even if we were to enrich their type systems, we would still have a lot of work to do to understand what exactly are the laws you need to verify. There's a lot more than sort of, than you might think at first. So this is somewhat problematic, and I think this is something as theoreticians we should be aware of, and find ways to think about this and to use it. Let me just give one amusing. I see I'm running kind of short on time. Let me just give one, I think, really shocking demonstration of the difference between what happens for algebraic structures in higher mathematics. So an example is the 3 sphere. So this is another example of when you have equality as proof relevant. The funny thing is you can start to make types that are kind of a priori a little bit silly. You wouldn't think of first in computer science, but that are interesting to think about, which is I can take a type and say it only has a single element, but there's a non-trivial element of its identity type. And this turns out to act very much like the circle. And so type theory with relevant equality has spheres. There are types which play the role of higher dimensional spheres. And in particular, the 3-dimensional sphere turns out to support a multiplication. Not all the spheres do, but this is another thing you can learn from topology. And you can ask how many how many A2 structures S3 has. So in other words, if I specify the data of the multiplication and the fact that it's associative, how many ways can I do that on the 3 sphere? And this is actually a known answer. In topology, there are exactly 12 ways of doing this. And you can ask a similar question: how many A infinity structures? So of those 12 structures, if I know the multiplication, is extending in higher dimensions unique? And the answer is really dismaying, because there are uncountably many A infinity structures, meaning that, so this gives you just a small taste of how big the difference is between finitely specified structures and infinite structures.
When you say how many A2 structures, you don't mean on the nose, you mean up to something, right?
I mean, well, up to homotopy, up to the natural notion of A2 structures being equivalent, which is that, the canonical notion of two A2 structures being.
Okay, and then in the A infinity case, you still mean up to
the same notion of equivalence, right? So I should have said, exactly.
If it's not up to equivalence, but it's not surprising there will be uncountably many on the nose, right?
I see. Okay, but right. Okay, no, I mean up to equivalence.
Clarifying whether we were quotienting by homotopy.
Yeah, up to homotopy. Up to homotopy, there are uncountably many, right? So exactly. So this is an example that shows that algebraic structures in this kind of setting are extremely rich, and we have sort of maybe not a huge understanding. And as I say, I think now I don't think in the next 10 years people are going to be counting the S3 structures in Haskell or something like this. What I'm trying to argue, though, is that being aware of these things, being aware of the way constructive equality behaves, is an important thing going forward to proposing type theories that that implement, that have rich notions of equality and that can express constraints in a nice way. Let me say, right, and so I think, so
could you wrap up in 5 minutes or something?
Yeah. Well, maybe I'll, so let me just in summary. Summary is that in constructive settings, equality behaves homotopically. That's what I sort of claim, and I think this is a robust claim, in the sense that even if you're interested in sets, in discrete objects, this perspective is useful or important. So for example, people trying to just describe type theories with strict equalities, I think many advances have been made since the introduction of homotopy type theory by understanding what naturally happens when you talk about constructive equality. Then you can see what you can do about strictifying it, or about forcing various equalities to coincide, or something like this. So another proof assistants which actually do force types to be truncated after some certain level, they take input from the perspective that there can be infinite many levels, and that we know how they behave. And also, so Martin Luff's rules proposes other implementations of higher equalities. So once you understand that constructive equality has this sort of interpretation as an infinity groupoid, then you can look at the rules of Martin Löf and realize that there are alternative rules that give the same structure, and you can start to modify those rules to be more well-behaved. So for example, people who've worked on cubical type theories, there are alternative rules in terms of confillers and things like this, which don't use Martin Löf's original proposal, but which have the same effect. And also by studying these other presentations, we may be able to describe presentations of type theory which are less onerous to work with. So for example, one of the complaints about this type of equality, this constructive equality, is it's extremely verbose. But once you understand what it's trying to describe, you can design systems where it's less verbose, where without destroying its important properties. So that's another thing that you learn from higher category theory and topology, how you can strictify or make it nicer to work with these weak structures without destroying their good properties. And so, yeah, so I think, again, the point of this talk was to argue that that these concepts are more robust than just isolated to proof assistance. I think if we look for how to treat equality precisely in ordinary programming languages, being aware of its constructive structure is important for designing good and useful such languages. Okay, so I'll stop there. Yeah.
Thanks so much, Eric. So now it's traditional for us to applaud, so please unmute yourself. Great. Now mute yourself again. Okay, now let's have some questions or even a discussion. Would be fantastic.
So I have a question. Well, actually, it's not a question. It's not even a comment. It's a request, Eric.
Okay.
So the background is that I'm the sort of person who I think probably thinks he understands the Martin Löf side of things quite well by now. Mm-hmm. I don't think I understand the other side of the coin at all. Mm-hmm. So my request is there somewhere a relatively straightforward definition of what an A-infinity space is? So what I don't want is what you get if, and I just did this now out of interest. So I went to NLab and I looked at A-infinity algebra. Definition 2.1. An A-infinity algebra is an algebra over an operad over an A-infinity operad. End of definition. Now that is not helpful.
Yeah.
Right. But is it possible?
Is it possible? So
I mean, I want something along the lines of a monoid is a set with an operation which is associative and has a unit. You know what I mean? So I'd like to know that an A-infinity space is a blah 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 with a blah 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 that satisfies blah blah blah. But
right.
It's not easy, is it?
Yeah. So unfortunately I think it's not possible to make it rigorous in that short a definition of time, right? So the standard definition from topology, so you need this notion of operad. So this is how people make this notion precise, to say that you have a huge number of different multiplications, but that they all amount to the same thing, that they're all homotopic to each other. And so the classical definition from topology is kind of the best one that I know how to say. So the problem is you have to make precise what are all the rest of the equations that need to be satisfied, right?
Sorry, can I ask related to this?
Yeah. So Andy, I guess the simple answer is that without describing the ways of parameterizing all the possible ways of associating in all higher dimensions, it's difficult to explain. But that's basically what an A-infinity space is. Step one, describe all higher dimensional associative laws. And step two, say that all of them coincide. That's what an A-infinity space is. Every higher dimensional way of associating two things gives the same answer. But in order to render that formal, you need the structure of what people call an A-infinity operad.
Marcel,
I think it would be a noble thing to chip away at that, to get something which was in the end explainable to a sixth former.
I totally agree with you. I totally agree with you.
I think that's absolutely possible. The idea that you need to understand the theory of operads to understand an A-infinity monoid is completely incorrect, I think.
Bogus. You say that it's
So but Eric, can I ask about general algebraic structures in higher dimensions? Which kind of thing can be axiomatized? Anything that is operatic and that's it, or
more than
even
that.
more?
I mean, these days, so the operatic ones are particularly simple. They're a nice class of algebraic structures. But by now, people can do higher Lever theories and things like this. So you can have algebraic structures with repeated arguments and this kind of stuff. I'm not sure there's. I know the limits of what everyone can do describing higher dimensional structures, but at least higher dimensional Lever theories have been studied. More complicated structures, I'm not 100% sure. Is that
okay? Yeah, higher the Lever theories. I haven't seen them, so I'll ask you for some points.
They exist, right? I mean, because once you have the theory of infinity categories up and going in a nice way, I didn't say what infinity categories are. You can start to define Lever theories, sort of importing the classical definitions. So I think there are papers.
Well,
I mean, there are subtleties. I'm not saying there are no subtleties.
Yeah, I'm not so. There are many subtleties because Lever theory is quite a strict notion. So you have to say you have a strict Cartesian category, or you take the free strict, and so on. So all this has to be transported to me.
So I should say that topologists, the structures that come up the most often. The structures that come up the most often in topology happen to be operatic, which is why the vast majority of, I think, effort has been focused on those structures.
Okay.
But I think that's a coincidence.
Okay.
So I'd like to say something which maybe is to prompt a discussion rather than a well-defined question. So there are a broad range of reasons why anybody might be, and I think if you look at the community of people who work on these sorts of topics, might be interested in these sorts of ideas. One might be interested in the foundations of mathematics, right? It's clear that's a big group of people who are interested in ideas in the sphere of your talk. One might be interested in homotopy theory, maybe doing formal homotopy theory, something like this. But that was not, Eric, the motivation that you gave.
That's
you
right.
Started really from like the perspective of a software engineer.
Yes. Yeah.
So I would like to my question, or the topic I'd like to propose for discussion is maybe not right now, but in principle, you know, if conjectures are true and if the area works out as we think, why might the future software engineer care about these sorts of ideas, and how might it change what it means for the everyday user of the everyday programmer, not someone who's a researcher in the foundations of mathematics, but someone who just wants to implement a bloody smartphone app or write a database service or whatever it is. Why in the future might these people care about these sorts of ideas? Or will they never be, right? Some people might say this is not part of computer science because this is just.
But I purposely sort of took that kind of provocative opinion because I actually think that's kind of true. And so let me just give some examples. So one example is the notion of algebraic data type, right? So the notion of algebraic data type, it comes from functional programming, but it's kind of suffused to the point where this is a really useful thing, and people admit it. So I just noticed, I was just reading last night as I was sort of like looking into these things, that the new Java, for example, has algebraic data types. Their recent update. Languages like Rust, these recent languages use algebraic data types and things like this. So programmers have recognized that this is an extremely useful tool, pattern matching on algebraic data types for organizing data and whatever. So what is the promise that sort of this higher algebra has for that? Well, the next step, I would say, is the funny thing about algebraic data types is they're algebraic, and they're always initial algebras for free monads. They can't express relations among their elements, right? They're always initial algebras for monads which are free. And what homotopy type theory sort of introduced is when you have a notion of equality, you can talk about types which are not free, types which have relations in them. Okay, so if I imagine implementing, say, an expression language, like I'm implementing a DSL in some language, and the first thing I do is I write that down in algebraic data type, which gives the expressions. But then I want to write an interpreter. And the interpreter is meant to treat certain expressions as equal to each other. So because, for example, if I don't know, if I have I'm writing an interpreter which is supposed to manipulate a cube on screen, and I have a small DSL for manipulating a cube, I can write a short language to rotate in various directions, but there are relations between the expressions for rotating in various dimensions. So what if I want to give a type to my function which says that it respects those relations, that it respects the non-unique, and this goes by the name of quotient types, right? So that's what I'm saying, is that once you have this notion of equality, your typing constraints can be more explicit. You can say not that I'm writing a function on a free algebra, but that I'm writing on a function whose input is an algebra which is not unique. And this is a huge boost in expressivity, right? So to be able to say, to type your function as a function whose input respects a certain relation among your expressions. And there's actually a dual version of that, which is that if you think of co-inductive types, there's a notion of higher co-inductive type where you impose relations. And co-inductive types are things that are like streams or like state machines and things like this. So imposing relations is specifying behavior. So having a type system which can have a function which specifies the well-formed behavior of its output is also a huge boost in expressivity.
So can I say it this way? So I think actually, so you say write functions on non-free types. I think we can trivially already write as many functions we want on non-free types, but we can't verify them at compile time.
Yes, exactly. So
right?
To the extent that you're looking for static guarantees of something like that, if you had quotient types, you can have a type which guarantees that any function using it must respect the equalities that you say. And I think my impression is that this notion of adding equality as data, having constructors for relations, and considering those as well-formed types, this is the notion of higher inductive type. This is by homotopy type theory, and this really sort of pushes us in the direction of really being able to do that, having the programmer have not only algebraic data types, but algebraic data types expressing also constraints.
So I'd 100% agree with the aspiration, and I think actually we're not far off probably achieving that, except that I wouldn't aspire to go beyond dimension 2 or 1, depending on what you're speaking. And so the thing that I'm unconvinced about is the necessity to foist on the programmer the full horror of high dimensionality.
So right. So
convince me of that.
So that I can't do.
Also,
I should point out that
also even at dimension. Let me just add one little thing, because also even at dimension 1 and 2, there are some programs that you want to write.
Marcelo.
Oh damn! We'll never know.
Well, go on, Andy.
Or is it the program that we want to write that will stop?
So, by the way, so just to finish.
He's back. No.
No, so what I was, okay.
Marcelo, you got cut off. Start again.
So I'll try to go somewhere else, maybe close to the router. So what I was saying is that we can define these quotient types now in some system at dimension 1 and 2. That's fine, but then you want to write some programs with these types, and from the few experiments I've been doing, mainly with Big Raman and really commutative monoids, it's quite, there are some programs that you try to write and the data type does not let you.
Yeah.
And there is a lot of extra work that you have to do to be able to write this program. So even if this is in place, it's unclear really how you actually use this stuff.
Yeah. Well, yeah.
And even I mentioned, on H sets. I mean,
yeah. I agree, but yeah. On the other hand, so what I wanted to say to answer Andy a little bit, two examples. So one, I meant to say it. The point of me talking about the example of graphs was exactly to say that graphs are a one type. So in some sense, every computer scientist already knows at least one higher dimensional type. The type of graph should really be considered as a one-dimensional type. So anyway, so that was my, but that's of course not higher than dimension one. So I didn't really respond.
Yeah, I mean, I was being purposely provocative.
No, sure.
Sure.
At first, I totally agree with you that I'm not sure I know the immediate examples, other than the fact that I think it's interesting that they exist. Well, I mean, I know the examples coming from topology, but it's not clear why a programmer would need them. What is useful to know is that if you want to quotient by a one-dimensional relation, if you want your type to be a one type, that you need to add infinitely many more.
Yeah.
That's not something that's obvious. That's not
Yeah.
something that's obvious. So it's not that the programmer uses that directly, but that insight coming from topology, that to truncate to something to make it a one type needs infinitely many relations, and that we can think about how to organize those relations. That's important, I feel.
Yeah.
So that's, I don't know if that's a concrete example or not.
Yeah.
I feel people don't talk about this enough. I think this is important for the viability of this topic as an area of computer science, right?
Yeah.
I'm going to pick on someone. I mean, Tim, next time you're writing some networking protocol, I mean, can we sell this to Tim? I mean, what if he could write his next networking protocol in homotopy type theory? What guarantees could he in principle? It feels like we're playing with toy examples still, and this is in principle, it's such a profound addition to our toolkit as programmers. We should be able to come up with some more sort of killer examples of sorts of computational capabilities that we should give rise to, because let's face it, these textbooks are pretty fat. So if we're going to tell people to read them,
well, I'm not sure that theory has reached its final form. I mean, like I say, I mean, I wanted this to be a motivation for, like, I think these things will eventually be useful. I guess maybe a way to summarize what I'm trying to say is that I think category theory had the same, many people question the importance of category theory as sort of suffusing into programming language, but that has clearly been a success. I mean, it's taken decades, but it's clearly been a success. And I guess my argument was, like, if we want to start thinking about equality, higher category theory should sort of play the same role. It's going to have to play that same role of, at first it's too abstract and we can't do anything with it, but we learn to do things with it, and those things slowly become useful.
So I have a thought, which is that, I mean, if I think back personally about my knowledge of dependent type theory, right, which I've kind of been, known about for 40 years or something, whatever, off and on. Yeah. But truly, with my hand on my heart, I and yet, roll forward to 2020, and I spend every day writing expressions in dependent type theory at the moment using a theorem prover. Now, why I wouldn't have done that until not recently. I mean, I could have done it earlier, but the reason I can do it, right, is not because of the nature of dependent type theory, because the things like the eliminator expression for identity types is an absolute bastard to use, right? But the reason I can do it is because there's this amazingly convenient pattern matching, right? So what we need for this high dimensional stuff is something, maybe not that, but something similar that makes it really accessible. Well, I mean, the underlying mathematical semantics might still involve, infinity operads or whatever, but somehow people can
I totally agree.
use it almost without knowing.
I totally agree.
I don't know. I don't know what that thing is though, because
Yeah,
this is
yeah,
quite
so
inherently
yes,
difficult subject.
that-
right?
that's something that I think about from time to time too. Is I
Yeah.
totally agree that the thing that makes these things accessible is the tooling and the packaging and this kind of thing. And I think that's an important part of why we can use dependent type theories today, because they are super verbose.
Mm.
And the thing that I didn't get to talk about today that Jamie and I have been working on is taking a toy model of all these coherences and figuring out what things we can strictify, what things we can simplify to make things less verbose. And I think that's an area of research that could lead to tools where it's not so painful all the time to work on this. But I agree, something like higher dimensional pattern matching, whatever it is, should definitely be invented. I'm sure it exists.
Yeah,
but
that's a very good thing. I mean, I'm absolutely happy to be as strict as I can be, as long as I, as
Sure.
it don't restrict generality too much. Yeah.
Sure. Yeah. The thing
Yeah.
is, you just need the theorem that says that you didn't lose anything. That's
Yeah.
the thing that's important,
Yeah.
right? It's, yeah. So.
Anybody else want to come into the conversation or maybe ask a different question?
I had a question about the talk. When you were talking about how a lot of time equality in programming languages is kind of ad hoc, but often there's a natural way to do it by recursing on the structure of the data type. And then you were talking about the number of monoids on a 3-sphere, how there were 12 in the A2 case and uncountably many in the A infinity case.
Right.
Is it sort of the case that there are maybe 12 natural A infinity ones, which are like the extension of the A2 ones, and then the rest are sort of different weird pathological cases because you have infinitely many choices or something like that?
I'm not sure exactly how to answer the question. So I can tell you where the rest of them come from. They are sort of weird choices, I would say. What you do, it's a topological technique. So I don't know if a little bit of topology says that if you have a topological space, you can actually force its homotopy groups to be local at a prime P. And so what you can do is take the 3-sphere and localize it at various primes. And then you can actually find out that there are H-space structures that are that the 3-sphere has at all sorts of different primes. So at the infinitely many different numbers of primes. And then what you do is you get a theorem that says that if you have an H-space structure at each prime, you can glue it together in a certain way. And that's how you get the uncountably many, because you can glue together the various H-space structures at various primes. So I don't know if you would consider that. So they are bizarre. They're manufactured in a certain sense to be unnatural because you mix what happens at different primes, but they're there and you can show that they exist. So
maybe perhaps if I ask in a slightly different way, if you start with an A2 monoid structure, is there like a simple way to extend it to complete it up to infinity?
No. Because at each step, when equality is structure, you need to pick the implementations of the next relations, and
right.
and the whole
there's nothing like there's nothing in like the machine which will let you pick something more natural.
No,
or anything.
No,
like
there's no just sort of canonical. Well, I should.
It may not be possible, right? For an A2 algebra, there may not be an A infinity algebra that truncates to it.
No, I mean, well, every A infinity algebra gives an A2 algebra by
Yeah, but I said the other way around.
Right, so not every A2 algebra need extend infinitely far. Right, that's right. That's right. But on the other hand, I should say there is a canonical is not a really word. Okay, so I shouldn't say canonical. There is a well-studied, an important H-space structure on S3, which comes from the fact that it really is a Lie group. So it actually has a coherent multiplication in every dimension. So that structure is singled out, but all singled out because we know how to define it, because it comes from the quaternions and people have thought about it, but not singled out in any other way.
Right.
Other than we know it's there because of the quaternions. But,
so you're saying it's well studied, but not necessarily more natural than any of the other choices?
Than any of the other 12. I mean, it's one of the 12, but why would the other 11 not be natural? So in general, no, there's no way. So the situation where there is a canonical extension is if you take a space which is truncated, right? So if I take a space which is truncated to some level and I have to choose the equalities at the higher levels, but because it's truncated, there's only one choice.
Yeah.
So, but the S3 is not truncated, so there's just not a unique choice, and there's nothing you can do about it.
Okay, cool. Thanks.
I have a question about these infinite number of coherence axioms you need to add in. So often it seems to be the case in presentations of type theory, people will say that a certain structure requires an infinite number of rules. But really what's happening is you have some higher order structure and you're parameterizing. And if you have that higher order structure, you can actually get over the finite presentation and it generates all of these infinite rules.
Mm-hmm.
So is it the case with these coherence laws that they can be generated from a finite set? Or is it actually, you can't avoid the fact that you literally need an infinite number and they don't come from some higher structure that's being sort of flattened down?
Yeah, that's a really excellent question. I would say it's not entirely clear, actually, because these, so you can parameterize things, these structures classically in set theory with sort of finite amounts of data. There are ways of doing that, but when people have tried to import various presentations of those things into something like homotopy type theory, they get stuck in sort of circular problems. And this goes by the name of the coherence problem. We can't even really define these structures very well in type theory yet. And so it's a little bit hard to say because this problem of like describing these infinitely many rules in type theory seems to run into problems that you don't run into when you do it classically in set theory. So how do you describe the difference? Would one be finitely presented and not the other? Or are we exploiting some structure? Or so, I mean, honestly, I don't know the answer to your question. It's not entirely clear, I would say. But the only presentations I think I know of these kinds of structures in type theory require co-induction or something like this, some specified infinite family. Yeah, we don't know how to present them in a sort of nice, simple, finite way yet. So maybe there is such a presentation. And I think lots of us would love to get our hands on something like that. Like if there's some simple finite presentation of the notion of infinity category, that would be great, but I don't know what it is.
Thanks, that's interesting.
Yeah.
Okay. So maybe we can leave it there. It's been really great to kick off the seminar series this term with such a great audience and a great talk and a great discussion. Let's keep it going for the rest of forever. Maybe we can thank Eric again. I can unmute everybody with a click, I think. Right. Thanks, Eric.